Alright, so we're going to be doing a combination of assembler with C today. We're going to do this on the PIC32, in this case the PIC32 MX250. And so I've started a project already. If you want to see how that project is made in the first place, look at the previous video, but I will go over a couple of highlights. Alright, so when you create the file, or when you create the project, what's important to point out is that the C version of the C file that you're creating is done the standard way. And the other thing that's important to point out is that when you do the assembler install or setup, you want to go into source files, new text, sorry, not text file, back, new, other, then you want to choose an empty file. And you're going to rename this file with a .S file extension, because .asm and .s don't work. They will not compile in this particular sort of configuration. All right, but I've already done that here. You can see it right here. It's assembler for main .S. And the file itself is written just like you would normally have a standard assembler file. The differences are, in this case, all my comments are in C style, so /* and then or double slash, right? And I have an include header here, which is totally the way you would do it in C, but not in assembler. And that's because I want to make sure that I get any of the definitions for my board or for my chip that are available from Microchip to get loaded up here in case that's required. From there, as I explained before, the .text refers to writing this part right here into the flash memory of the chip. I don't want the assembler to do any optimization or whatever, so I tell it not to. And then, and this is really key right here, in order to sort of connect your assembler and your C together, is to say that this right here, this symbol, ASM function, is the name of a function. And that when I call the function from C, this is where the compiler should be pointing to in terms of memory. Because really a function, all it is a label in a bunch of numbers written inside of your flash memory. It's a label, and the CPU, the chip, the microprocessor needs to know where to jump to in memory, and it's gonna look at the sort of the address related to or associated with this. All right, so let's get started here. I'm gonna put some breakpoints in right there. I put a couple of other breakpoints in there as well, but let's fire up. All right, so over here you can see that I've got my configuration patterns set up. If ever you need to change that because you're using some other PIC32, then you go into configuration bits down here, and you can do a sort of a generate code to output. You can actually set all of this up and send it out to a text file and copy and paste it right in here. All right, what else? Here is the prototype for the assembler function. Notice that it's been defined as extern, so it's sort of external, and it has no output, and it has one input. That input is a number that gets sent in, and you can set that up in any way you want. It will take that value and it will load it into sort of a transfer register called A0. All right. Next up, yeah, there's the call rate there. So let's fire this up. All right, so I'm now hitting the breakpoint right here, and I've gotten to the first math example that is listed in the assembler code. So what this is you load two values, 2 and 1, into registers. You're going to add them together, and then you're going to take that result and you're going to exclusive OR it with another bit pattern. That's what this chunk right here is supposed to be doing. Now, a couple of little tricks with the PIC32 MIPS style processor. In order to take an immediate value, which is sort of that numeric value, and make it available for calculation, you have to use something called an add immediate unsigned assembler instruction, and you take the numeric value that you want, you add it to the value 0, and then it gets stored in that register right there, the one you specify right there. It's weird, I know. That's how it's done. Next up, we're going to store 2 in T0. We're going to take 1 and store it in T1. Then we're going to do adding of T0 and T1, and we're going to store the result in T2. Then we're going to take another value, store it in T3, and we're going to do exclusive OR of that new value, which is in T3, with the result of this summation, which is in T2, and we're going to exclusive OR them together and store the result in T4. So let's step through. And we're going to look at the registers right there. You can see that T0 was just updated with the value 2. You can see right there. Next, you should see 1 appear right there in T1. There it is right there. We're now going to add them together, and the result should end up right there in T2. It'll wipe out the 32 that's already in there. And so 2 and 1 together is 3. We're good. All right, that value right there. Next up, we're going to put in a new value into T3. You can see right there, so 3. And we're going to exclusive OR the 2 together. And that goes into T4. T4 didn't change because it was 0 before. It's still 0. It didn't update. That's because you exclusive ORing basically the same binary values together, 1 and 1, twice. Okay. Next up, add 2 binary numbers and AND them. So this is the logical AND. We're going to AND them down here. So store 2 numbers in T0, T1. We're going to exclusive OR them and put the result in T2. Then we're going to take a new value, put it in T3. We're going to take T2's value and T3's value and store the result of an AND operation in T4. So step, step, step. So T0 got updated, T1 got updated, so the 5 and 11. Next up we have T2, which has been updated to 14. We've put T3, a value into T3 of 5, and now we're going to AND everything together, and that gets stored in T4. There we go, it got stored in T4. Next, add 2 numbers using 3 temporary registers. Okay, so the temporary registers are T0, T1, and T2. We're putting hex 11 and hex 22. So you can put a decimal base 10 value into any register you want. You could put a hexadecimal value in there or a straight out binary value. It doesn't matter. To the machine, it looks exactly the same. You just put whatever's convenient for you. All right. So 2 hexadecimal numbers, which will get converted by the machine into binary. And we're going to add them together. So we're going to take 11 in hex, 22 in hex, and add them together. And that should give you a hex of 33, or what would it be in base 10? So we've got 34 and 17 together. So added together, that's 50, 50, 50 something, right? 51. So it's 51. Okay, then subtract 2 numbers using 3 temporary registers. All right, so we're going to take the same values we had before. We're going to put them in T0 and T1. All right, that doesn't change because they were already the same. Now we're going to subtract 17 from 34, which should give us 17. And 17 got put into T2. Next, AND 2 numbers using 3 temporary registers, T0 and T0, T1, and T2. So again, we're using the same values. We're putting them into T0 and T1, and we're going to AND them, logical AND together. Okay, and you can see that T2 ended up having a value of 0 after that logical AND. Next, OR them together. 51 is the result. Next, multiplication of 2 numbers using 4 temporary registers. All right, what's going on here? So 4 registers, T1, T0, T2, and T3. Watch what happens here. So we're going to take this, we're going to take 5 and 4 and multiply them together, which should give us 20, right? So I'm looking at mult U, which is going to have these, that T1 and T0. We're going to multiply it together. We'll get 20 in there, right? Let's check it out. T1, what happened to T1? T1 still has 5. T1 has 4. T0 has 5. What happened? I should have read the comment. All right, the comment said T1 and T0 multiplied. The result is stored elsewhere. It's shoved to a different place. And then we have to retrieve the values. Okay, so we use MF high and MF low to get the high part, so the highest value part of the multiplication, and low to get the lowest part, because they're sort of concatenated together. And I'm going to grab the 2 and I'm going to store those in T2 and T3. So T3, I believe, will have the value of 20 in it. Let's check it out. Oh, there you go. All right, so T3 has 20 in it. There wasn't anything in T0 because the multiplication wasn't that big. All right, we're going to do the same thing with divide. Now, there will be an issue here. I'm not sure. There's a little bug when we go through this where I have to do multiple steps to get past line 109, but you'll see. Anyway, it follows the same process as multiplication. All right, so 2 and 9 together. We're going to divide. Okay, so MF high. Step, 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 step. Come on. And low. So what's in T2 and T3? So T2 gets a value of 1 and T3 gets a value of 4. All right. So that's because there's a remainder that goes into T2. So there's your remainder right there. And the quotient goes into T3 right there. So the division actually uses those two separate registers, well, those two separate values that then get stored in two different registers as the value for remainder and quotient. All right, so that's how you can deal with integer style division. Okay, and the rest is something that we did already in a previous lab. So we skip, skip, skip. We get to the epilogue. This is where we bring stuff out of the stack and return the stack to its previous value. And then we jump back. You can see we've jumped back. We came out of the assembler function and we're now in the while loop. And there you have it, doing math operations in while assembler, but having called it from C. And this, to me, in my mind, is a usable way for dealing with assembler, where you basically compartmentalize your assembler work into one section of your code, into a separate file, and you do all the rest of your work, the stuff that you maintain on a regular basis, and that in C or maybe even C++. And so when you call up the assembler as needed, but you really hive it off, you separate it out so so that it's by itself easier to maintain as well. All right, there you go, assembler in C doing some math.